All right, everybody. We have 2 weeks left. I will candidly admit that after lecture today, I'm going to be a little bit off script for the rest of the semester. In other words, Marshall extended their calendar by a week. And when I did that, or when they did that, I decided to take a look at steel design. And there were a couple of topics that I eliminated because, not really that they weren't important, but I didn't really think they fit into the broad picture of everything that we do in the nature of steel design. So I sort of eliminated those because I wanted to give myself more time at the end. And this is actually the last lecture that I taught last year, and then we would do exam review. So for the next 4 lectures after this, I'm sort of going on autopilot a little bit. We'll just sort of see what happens. I'm still got some stuff I'm working to prepare for those 4 days, but I kind of want to talk more big picture. And I've debated whether or not I want to talk about composite beam design. I've never taught composite beam design in undergraduate steel, but it's a really important topic, and I might talk about it. But I have homework 7 assigned today. This is going to be our last. Well, I don't know if it's our last assignment, but it very well may be. Like I said, next 4 lectures, I haven't yet decided what I'm going to do. Okay. But I'll keep you posted. But I will say this about homework 7. Homework 7 is short. It's a pretty quick assignment. Okay, did everybody get the code? Okay, so today what we're going to do is we're going to talk about something that I've been ignoring all semester, which is the idea of local buckling. And I'm sure if there were any, I don't know, I guess, steel design professional or professors out there following these lectures, which I'm sure there are not, but if there were, they'd probably be, wagging their finger at me like, you haven't talked about this. How come you haven't talked about it? I tend to think it's more educationally instructive to talk about it, but to talk about it at the end, because at least for the vast majority of what you discuss in column design and beam design, local buckling, if you were to integrate it, would be, I guess, a formality and a time suck at the same time, and I'd rather just talk about it afterwards, now that we kind of have an understanding of what's going on with buckling. So let me just get right into it, okay? And let's just sort of recap what's going on with buckling. Okay, so I have 2 sort of scenarios with buckling that I've been talking about all semester, and these are the ideas of column buckling and beam buckling. Both of them incur some degree of bending, but essentially column buckling happens when you take an element and you load it in axial compression, so load directly through its centroid, and when you do that, it buckles according to the following pattern. We either have an inelastic buckling state or we have an elastic buckling state defined by where our slenderness falls along a given axis or along a given range. So the idea is that let's just sort of maybe look a little bit more big picture at stability and buckling in general. Whenever we're looking at a buckling problem and we're trying to determine capacity, what we do is we take a look at an element under consideration. We ask ourselves how slender that element is. Remember, L over R, that's a slenderness limit, or a slenderness measure. Not a slenderness limit, it's a slenderness measure. It's a measure of the slenderness of a given component. And then we take that measure and we compare it against a given capacity model to determine whether or not we're in one zone or another. And then based on that zone, we assess capacity. And whether we're talking about columns or we're talking about beams, it's the same idea, okay? With beams, what we do is we check the x-axis. So in beam land, we've sort of written it in terms of LB as opposed to L over R, because with beams, the beam curve itself is so darn complicated that we can't really write a single unique graph that applies to every beam in the spec. Now we can do that with columns, right? And so with columns, what we do is we divide out that R, so we get that L over R term, because this curve really works for any column in the book. Now this curve does too, but because it's so multi-parameter, there's so many different parameters that go into the beam curve, we know that there's a unique beam curve for every beam, which is why we just go with LB. But it's the same idea. We take a look at effectively our slenderness, and we compare that against our curve to see what range we're in, and based on that, we determine our capacity. But both of these curves, whether it's the column curve or the beam curve, both of these curves have a latent assumption baked into the background, and that latent assumption is that local buckling does not happen. Or at a minimum, I guess I should say, local buckling doesn't happen first. If you go down to the lab and you start testing columns and testing beams and what have you, what you find is that, you know, if you were to take a beam section and start loading it, and I mean, you load that thing to where it goes to the floor, you know, I mean, you bend that beam like crazy, what you will find is that failure is usually a mixture of global buckling and local buckling. It's just a question of which one happens first, okay? And this entire semester we've been assuming, although we haven't really been talking about it, but we've been assuming that global buckling happens first, and we haven't really been considering ourselves with the idea of local buckling. So what is local buckling? Best way to show you what local buckling is to show you some pretty pictures. So here's some pretty pictures, okay? So I have here a column, okay, and this column is undergoing compression, okay? Now I have two images here of the column, these sort of rainbow plots, and I'll start off by focusing your attention on the image to the right, okay? So this image to the right is an example of what we would call global buckling, okay? So with global buckling, the idea is that the flange, the top flange, the web, and the bottom flange all act as one. We take that column and we load it, and it experiences a sudden lateral deformation, and the whole column translates, right? So if we were to samurai sword or lightsaber through the cross section, either before it buckles or after it buckles, we would still be looking at an I-shaped cross section, right? Really, with global buckling, what happens is the whole cross section, the whole letter I, as it was, the whole letter I just shifts over, right? That is an idea of global buckling. And in most routine building-based column design, global buckling is what's going to govern. But it's not always the case, okay? Here is an example of what I would call local buckling, okay? So in the case of local buckling, what's happening is it's not the entire column that's buckling, it's just a flange, or it's just a web, okay? And if you samurai sword or lightsaber through a random cross section here, what you're going to find is that it's no longer looking like an I shape. In fact, what's happening is the actual cross section itself is deforming in some way, shape, or form, okay? So what's happening is the individual plates, the flange, the web, they are the ones that are guarding the idea or governing the capacity, okay? Here's sort of an image of a local buckle. I'm cheating a little bit with this image, but I guess maybe I'm making a point with it as well. This image is of a steel framing system, and you can see, it's a little difficult to see, but see how you've got this like flange sort of warping right here? That's a local buckle. Here's one right here. Now the reason why I'm cheating a little bit is because it's very common that steel will get more and more unstable under a fire, okay? So this is a local buckle that was present under fire conditions, okay? So it's not normal operating, hence I'm cheating a little bit. But, you know, you have fire. Fire tends to lower your E value, and well, what do you think is going to happen here, okay? So I'm going to pause my recording here real quick because I want to show you these videos. So, all right. Does that make sense? That makes sense? Okay. Now, like I said, the big question about local buckling is it going to occur before global buckling, okay? And the answer is no, you can sort of ignore it because the idea is, I mean, let me put it this way. If we were going back to tension members, I go back to tension members a lot, and we were looking at gross section yielding and net section fracture. Let's just think of those two limit states, gross section yielding and net section fracture. If I find that net section fracture occurs before gross section yielding, like the net section fracture capacity is 200 kips, gross section yielding is 300 kips. If I find that net section fracture occurs before gross section yielding, I can ignore gross section yielding. That doesn't really matter anymore, right? What matters is the limit state that governs. Now what I'm saying is that for the vast majority of elements that we've been looking at, local buckling hasn't happened first, but there are instances where it could happen first, okay? Now, in general, if you don't know, then you need to establish that first. Now, I'm not one to, I'll admit one of my pet peeves is when I'm in a presentation and somebody who's presenting their work goes back and says, you know, I did this during my research, and then it has absolutely nothing to do with their topic. They just wanted to talk about their research, you know, look at what I did. So I really don't talk about that very much in class, but this one instance I thought it was pretty relevant to mention this. So this was a plot that I pulled out of my dissertation, and what I was doing was I was trying to characterize the flexural behavior of a what we call a press brake form tub girder. So the idea behind this U-shaped beam here was instead of using like an I shape, like a W section, the idea was to take a standard mill plate of steel directly from the mill. Standard plate, structural plate comes in standard widths, like 72 inches, 84 inches, 96 inches. And the idea was to bend it into a U-shaped girder, stick a concrete deck on top of it, and use that as a girder for a short span bridge application. So what I was trying to do, so we were trying to apply that, you know, as a modular system for accelerated bridge construction. And one of the things I was trying to do in my dissertation is I was trying to figure out what is its capacity, like how do you calculate the flexural capacity of a beam like that? Because you need to do that in order to be able to design with that beam. So what I needed to do was I needed to assess, is it going to be governed by local buckling or is it going to be governed by global buckling? Okay, so I did a lot of fancy finite strip analyses to assess that, and I found that local buckling is essentially not an issue. And I'll explain what I mean by that by looking at this number 1.52. So in a nutshell, what happens in the spec is what we do is we take the width to thickness ratios, which are essentially the slenderness ratios of the flange and the web, and we compare those against specified limits. Kind of like how we calculate column capacity and beam capacity in general. Like let's say column capacity. What do? We take the slenderness of the column and figure out what zone we're in. Here what we do is we take the slenderness of the flange or the slenderness of the web, and we try and figure out whether or not we even need to consider local buckling at all. Okay? Now how do we establish those limits? Well, in a nutshell, what we do, like let's say we're talking about a column. Okay, so what we do is we say we've got a column, let's look at the slenderness of the flange or the slenderness of the web, and let's figure out how much, what is the buckling stress for that flange, for that web. Take that buckling stress, set it equal to Fy, and back calculate what is the slenderness that makes that happen. That's basically how we set up all these limits in the spec. So in the case of a column, we're comparing the load against Fy. In the case of a beam, we're essentially comparing it against My. Now what I found was that for these elements, local buckling, so here you can see this is sort of a local or a distortional type buckling effect, so you can see the flange is starting to give, this flange is starting to give here, the web's starting to bow out a little bit. That didn't happen until we got right here. This was my worst case scenario. And that worst case scenario was about 50% over My. So basically that told me that I didn't really need to consider a local or distortional buckling for my capacity, and really the only thing that mattered was the global regular old LTB we've been using this whole time. And so that was one of my findings in my dissertation. Now, so I wanted to mention it because that method is basically the same thing that AISC uses in the establishment of limits for local buckling for columns and beams. So how does this work? So if you go to any of the, let's just limit our discussion to W sections. So if you go to any of the pages for W sections, we have what are called compact section criteria. Okay? And for those compact section criteria limits, what we list is a ratio BF over 2TF and a ratio H over TW. We've already used this one a little bit because we used that one for shear, right? Now, what these are the slenderness measures, bless you, the slenderness measures of the associated plates of a cross section. Okay, so if we're talking about an I shape, so for example, H over TW is the width to thickness ratio of this plate, right? So the bigger that H over TW is, the more slender or the more flimsy that plate is, okay? In the case of a flange, what we're worried about is not the entire flange, we're sort of worried about this outstanding element of the flange here. Like think of this as a boundary condition and this is a free end. So what we care about is this width over this thickness, and so that's half of this divided by TF. So that's why there's that 2 there, okay? And so again, the idea with the flanges is the bigger that number is, the bigger that ratio is, the more flimsy the flange is. And so now we're trying to figure out, okay, this is how flimsy the flange is, this is how flimsy the web is. Is it flimsy enough that we need to start considering local buckling or not? How do we figure that out? Well, the spec made that really easy for us, okay? Remember with columns, we have a zone 1 and a zone 2, and with beams, we have a zone 1, zone 2, and zone 3. Same idea with local buckling as well. So in the case of columns, if we're looking at a column, like a W section under compression, and we want to figure out what's going on with the flange or what's going on with the web, we either determine whether or not that flange or web is slender or whether it's non-slender. And by the way, if you hear me using the term non-slender or compact, that kind of means the same thing. So the idea is like, here's compact, and here's slender. Yeah, kind of the same idea. Now imagine, just for like sake of discussion purposes, let's say these two cross sections had the same area, the same moment of inertia, the same radii of gyration. If those properties are the same, then I guess theoretically they would have the same capacity. But I imagine something in your gut tells you that this section is stronger than this one because these elements are flimsier, right? That's kind of the idea, right? Now in the case of columns, we either have non-slender elements or slender elements. In the case of beams, we have 3 zones. Just like we do for global buckling, we have 3 zones of local buckling. So for a given flange, we could have a compact flange, we could have a non-compact flange, or we could have a slender flange, or we could have a compact web, non-compact web, or slender web. So what I would tell you is that without knowing it, this whole semester, we've been dealing with sections that had compact flanges and compact webs. We just didn't know it because we hadn't talked about it yet. So now we can sort of talk about it. Now, where do we get these anchor points like this lambda P and this lambda R and stuff right here? We get them in the spec. So this is in chapter B, okay? So this is on 16.1, I think, what did I skipped the page. It's on 16.1-21. I would open to that right now. So this is in chapter B. This is the general requirements that pretty much every shape needs to assess. Now there's a table B41, okay? And that's split up into 2 sections. There's a B41A and a B41B, okay? I want to make sure everybody can find this. So, and I think the B41B table actually goes across 2 different pages, like there's a front and a back, okay? Is everybody able to find that? Looks like most people are able to find it. Okay. Now, like I said, so there's 2 tables, B41A. So what does it say? Width to thickness ratios, members subjected to axial compression. So B41A, that's my column table. B41B, members subjected to flexure. That's my beam table. Okay. Now, one thing I did kind of gloss over a little bit, as I said, so there's a table for column and there's a table for beams. But look over here on the very, very left. So like on the column, it says there's a range of cases for unstiffened elements and a range of cases for stiffened elements. So what's the difference between those two? Okay, so unstiffened elements are elements that would only, plate elements that are only supported on one edge. So an example of that would be like the flange of an I shape. If we were talking about angles, like the leg of an angle, like so if you have an angle, it's like here's the angle, it's supported on this end but not this end. Or if we're talking about this leg, it's supported on this end but not this end. Okay. What about T-shapes, the stems of the various outlying elements of the T-shapes? Those are unstiffened elements. Stiffened elements would be elements that are supported on both edges, things like the webs. Okay? So in the case of a W section, the stiffened element is going to be the web, the unstiffened element is going to be the flange. Okay? Does that make sense? All right. So when we go to the spec, if we're looking at columns, we have a series of cases of unstiffened elements, a series of cases of stiffened elements. For beams, a series of cases for unstiffened elements, a series of cases for stiffened elements. And what we would do is we would classify those sections based on their behavior under compression and based on their behavior under flexure. Okay, and to show you how that works, let's do a quick one. Okay, so let's classify a W14 by 99. Okay, so I'm going to need your help on this one. Okay, so let's classify a W14 by 99, and what we're going to do is we're going to classify it according to both compression and to flexure. Okay, and by the way, I'm sure some of you could read table 1.1 and sort of see where this is going, but even if you read table 4.1 or table 1.1, it doesn't give you all the details, and so you do end up needing to do this even if you know the section is classified one way or the other. So there's really no other way of getting around it. Okay. Now, let's start off with this. Okay, so I want somebody to look up the properties for a W14 by 99, and what I want you to tell me is this and this. Okay, so by the way, if you see me call them lambda F or lambda W, that's what those are. Lambdas are your dimensionless slenderness parameter that are often used in steel and stability calcs and whatnot. So what's my flange slenderness?
Lambda F is 10.2.
10.2?
Oh, my bad.
9.14? 9.34. Okay. What about H over TW?
23.5.
Okay. So 9.34 and 23.5. Okay. All right. So, okay. Now what we're going to do is, so I just need those values off to the side. Now what we're going to do is we're going to start classifying. Okay. Now, I'm going to start off with the easiest one first, and we're going to classify according to compression. Now, when I say I'm classifying according to compression, what I'm basically saying is if I were to use this W14 by 99 as a column, okay? Whereas after this, what we'll do is classification according to flexure, which is what if I were to use this as a beam, okay? All right, so let's open up the spec. Okay, so we're in chapter B. Okay, I'm at this table. Okay, so width to thickness ratios, compression elements, members subjected to axial compression. So I have unstiffened elements and I have stiffened elements. How many cases do I have for unstiffened elements? I've got 1, 2, 3, 4. Do I need to consider case 4? No. Case 3? No. Case 2? Okay. What about case 2? Flanges of built-up I-shaped sections. Is this a built-up I-shaped section? No. A built-up I-shaped section would be like a plate girder where you take a plate, and you weld them together. That's not a W section. A W section is rolled out of the mill as a single I-shape. So do we consider case 1? Yes. Flanges of a rolled I-shaped section. Yes, we are considering case 1. Okay? So our width to thickness ratio, B over T. What is the B over T? Well, it's this, right? Which is what we looked up. Okay? What do we compare that against? This right here. Remember how I said a number times the square root of E over Fy is going to show up a lot? Well, I meant what I said. Okay? So, all right. So let's look at lambda R. Okay? I'm going to call it lambda RF for the flange. Okay? So this is, what did we get? What did it say here? 0.56 square root of E over Fy. what is this?
13.49.
13.49. Okay. Now, what does this mean? Okay. Let's sort of think about this. Okay. Okay. So I have BF over 2TF and I have lambda RF. What I'm finding is that lambda RF is bigger, right? Okay. So let's sort of think about this a little bit. Okay. So this is a measure right here of how flimsy the flange is. This is a measure of how flimsy the flange is. This is an anchor point. And what this point is saying is that if your flange is flimsier than this, then you need to start considering local buckling. So my question for you is, do we have a flange that is slender, or do we have a flange that is compact? It's compact, right? Because this is what this is basically saying is if your slenderness gets bigger than this, it's flimsy and we need to consider it slender. But our slenderness value is this. So because that's smaller, this is a compact flange. And I'll say in compression. Okay? So what this is saying is if you use a W14 by 99 as a column, you don't need to worry about the flange buckling. Okay? What about the web? So I ask you to open up your spec and tell me what is lambda RW going to be? First off, are the webs unstiffened elements or are they stiffened elements? Okay. So if we have the web of an I-shaped cross-section like a W shape, like a W14 by 99, what is my slenderness limit? 1.49. Okay. So just to make sure we're all on the same page, we're down here in our stiffened elements. We go to case 5, web of a doubly symmetric I shape. Right there, 1.49. So what is this? 35.88. So now we have an H over TW, which is also less than the limit. So what does this mean? Do we have a compact web or do we have a slender web? Remember, with columns, we just have compact or slender. There's no third range. Compact. Okay. So what this is saying is, okay, let me ask you what it's saying. Do I have to consider local buckling for this shape if it's a column? No, I don't. Okay, so what this check is essentially saying is, remember all that column stuff we did a few weeks ago? You can do that column stuff on this column, and it's A-okay. You don't need to consider local buckling for a column if it's a W14 by 99 of 50 KSI steel. Don't have to worry about it. So I wonder what's going to happen if we classify according to Flexure. So now what we're going to do is we're going to say, okay, let's not use the W14 by 99 as a column. Let's use it as a beam. So imagine using a W14 by 99 as a beam in a building. How do we classify according to Flexure? Well, we go to this, go to members subjected to Flexure. I'm going to zoom out a little bit. These are all of our unstiffened elements. So which case do we do? 10, 11, 12, 13, 14?
10.
10. Flanges of rolled eye shapes. So we have these two limits to assess. 0.38, 1. Okay? So, because remember with beams we have 3 zones. We're trying to figure out what zone we're in. Okay? So we're going to have a lambda PF and a lambda RF. Lambda PF and we have 0.38, 1. Would you all trust me if I just gave you these answers right here? Okay, so this one, 9.15. We have 24.08. Remind me, hold on. What was that?
9.34.
9.34. Okay. So hold on, let's see. So that means our flange slenderness is between these, isn't it? So if your LB was between LP and LR, you would say you're in zone 2, right? So do we have a compact flange? Do we have a non-compact flange? Or do we have a slender flange? Non-compact. We're in between, okay? So non-compact flange in bending. Okay. Now what about the web? Okay. What case are we going to be dealing with the web? 15. So we're going to have 3.76 and 5.7. So let's see what we get here. Okay, so 3.76 and 5.7 times the square root of E over Fy is another one of those cases where if I give you the value, you'll trust me. Oh, it would help if I didn't go away. Okay, and by the way, what was our H over TW?
23.5.
23.5?
Mhm.
I think this marker is done for. I don't know how I made that, but I did. So, what zone are we in this case? Compact, like zone 1, right? So, because this is saying, or here, maybe I'll write it like this. Okay. Maybe I'll put N answers. If I could write an S more clearly. Okay. All right, does that make sense? Okay. Now for the next couple minutes, we'll have sort of a movie time type thing where I can show you what happens here. But before we move on, any questions? So I'm giving you another classification problem here, but I want to say a few words about this problem. Okay, which shape was this? A W14 by 99? Okay, so if we go to the manual, so here's the manual, and we go to the W14 by 99, what do we have here? We have a W14 by 99, but there's this little footnote right here, right? The little F. What does the F mean? Well, if we go to the bottom, it says shape exceeds the compact limit for flexure with Fy equals 50 KSI. Doesn't quite tell you if it's the compact limit for the flange or the web, but it does exceed it, right? And so we're going to have to handle that in some fashion. Okay. So let's talk about handling that. Okay. Let's talk about that. Okay. I want to go to the spec, and let's do beams first. Okay. Let's look at beams. Okay. So now that we have a little bit of a larger picture with this stuff, let's read this a little bit. Okay. All right, this is chapter F. I want to read section F2. Doubly symmetric, compact eye-shaped members and channels bend about their major axis. So what F2 is saying is that both the web and the flange are compact in bending. Okay? So how about this? F2, compact, flange, compact, web. Okay? What does F3 say? F3 says doubly symmetric eye-shaped members with compact webs and non-compact or slender flanges. Okay. So F3, non-compact or slender or compact web. Okay, so let's just sort of review these specs a little bit and see what's going on here. Let's look at section F2. And I'm going to get to that user's note, by the way, here in a bit. I skipped over that. That's kind of important. Okay, F2. Okay, first off, does the stuff in this section look familiar? Okay, this is section F2. We have two limit states to assess. We have yielding, we have lateral torsional buckling. What's the deal with lateral torsional buckling? When we're in zone 1, we don't apply LTB because we just use that. When we're between LP and LR, we use that. When LB is greater than LR, we use that. This should look familiar, right? Okay, this should look familiar. This is what we've been doing this whole time. And I propose what we've been doing this whole time works fine and dandy if the section is compact. Now, what does this little user note say right here? For Fy equals 50 KSI, all current ASTM sections except these have compact flanges. It's almost like I engineered this problem for that not to be the case. So how do you handle a W14 by 99? Because it has a non-compact flange, does that mean if you put a feather on it, the beam explodes? No, it doesn't mean that. All it means is that you just have to use a different section of the spec. We have to use F3, okay? So what's the deal with F3? It's just different equations, right? It's a different model. We have, for sections with non-compact flanges, we use this equation instead, okay? Very plug and chug. So much so, let's take a look at this. So I posted this to Blackboard, by the way. So let's compute the flexural capacity of a W14 by 99 if it's 50 KSI steel, and we'll assume that that LB is 0. Let's just assume that. Okay. So how do we do this? So the first thing we do is we look up some stuff. We've already looked up these two, right? Okay, we've already looked up these two, and I looked at these because I'm going to need them later in the problem. Okay, the first thing that I have to do is I have to classify the cross section. Okay, I literally just did this for you all just now, right? We have lambda PF, lambda RF, lambda PW, lambda RW. We know it has a non-compact flange and a compact web. So if that's the case and you have a non-compact flange, all you do is calculate your MN capacity like this. We have to calculate MP in this expression. MP is FYZX. I'm leaving everything in inch kips right here because I'm going to have this right here. So 0.7 FYSX. So this is MP. That's that term right here. Plug and there you go. Okay. There is sort of a reason I'm not doing this problem explicitly for you here on the screen. Some of you are graduating here in a couple weeks. Some of you got a little bit longer. But the point is, you're all going to be working as engineers doing problems that I never taught you how to do, because you do kind of need to be able to research the spec and follow this stuff on your own. Like, my suggestion for you would be to take this example, go to the spec, and see if you can follow along what I'm doing and why I'm doing it, okay? If you could do that, then my point is you could do other problems the same way, okay? And I'll say this, I don't want you to think that you're being cast into the wilderness here, because the spec does a really good job of making it easy for you. I told you I was going to go back to this. Let's look at this, okay? If your beam looks like this, and this is compact, and this is compact, use section F2. If your beam looks like this, and the flange is non-compact or the flange is slender, use that section. It's literally giving you pictures to show you how to do this stuff, okay? All right? For example, okay, now that's beams. Let's go back to columns, okay? Let's read these sections of the column spec, okay? So what do we have here? So E1 is general provisions, E2 is how to calculate effective length, E3, we've been using E3 this whole time. Flexural buckling of members without slender elements. What is E3? Let's go to E3. I don't know about you, that looks kind of familiar to me, doesn't it? Right? That looks pretty familiar to me. Okay, so what's going on here? So here's E3. E4, torsional buckling. That's if you're trying to assess if the element's twisting. We're not really worried about that here. Single angle compression members. That's if you take an angle and put it in compression. So for you folks who are doing the bridge, if you had a member in compression, you could actually calculate the capacity this way right here. Built up members. That's plate, web, plate, plate girder, things like that. E7. Members with slender elements. So what if you had to calculate the capacity of a column with slender elements? Let's calculate the capacity of a W21 by 44. We'll assume that the column's pinned on both ends and it's 10 foot long. So we know what KL is in either direction. How do we do this? The first thing we do is classify the column. We find that it has a compact flange, but it has a slender web. Then what do? We just follow the spec, okay? Now, I'm going to let you all follow this on your own, but I'll give you at least a little bit of guidance. So ultimately, actually what we're trying to do is this calculation right here. So the way that the spec handles column buckling is if you have a slender element, what it basically says, so in this example, we have a slender web. So basically, like here's your cross section, right? But instead of using the gross area, what we'll do is use like this area, okay? And we'll call this area the effective area, because basically what it's saying is that this part of the web right here has probably like buckled and is kind of worthless. So we're only going to consider the section of the eye girder that's effective to resist the buckling capacity. So all we're doing is calculating this reduced area because of the buckle, okay? It's a little bit more involved, but I'm not doing anything here that you couldn't just follow the spec, okay? It's really not that difficult. Any questions? All right, well, I'm going to pull up the code one more time. That's all I got, everybody. I will see you all on Wednesday.